Chemists will often talk about the electronic structure of an atom or molecule. And by electronic structure, what we mean is how electrons are organized. And the reason why this is so important to us is because it is through electrons that atoms interact with one another. So electrons are described as residing in what we call the extra-nuclear space of the atom. That is, they exist outside of the nucleus. An important thing to recognize is that the nucleus has a positive charge and electrons are negatively charged. And what that means is that electrons will be attracted to the nucleus. So with respect to energy, what it means is that it takes energy to move an electron away from the nucleus. And the net result of this is that the further away an electron is from the nucleus, the greater energy it has. So the higher energy electrons are found at greater distance from the nucleus than lower energy electrons. So an electron that is closer to the nucleus is lower in energy than an electron that is further away. So this guy here, his name is Erwin Schrodinger, super interesting guy, developed what is now known as the Schrodinger Equation. And the Schrodinger Equation is useful because it can predict how electrons are organized around the nucleus of an atom. And this is a quantum mechanical model, which means that it's a statistical model. So statistics can kind of be a little bit weird, and probably the most famous example of sort of quantum weirdness is the concept of Schrodinger's cat, which is a thought experiment that Erwin Schrodinger came up with to illustrate some of the sort of the weird results that can come from his model. So we may as well talk about Schrodinger's cat because it's just kind of fun. And so this is the thought experiment that Schrodinger came up with. So you have a box, it's a wooden box in this case, and it is divided by a barrier that can allow a gas to pass across it. And in one half, on one side of this barrier, you got a cat. Meow. There he is. Okay, there's a cat. And then on the other side, you have this really elaborate setup. What you have is you have a Geiger counter. And the Geiger counter is connected to a hammer. And if the Geiger counter gets activated, the hammer goes off. And the hammer falls down. And what the hammer hits is a bottle, a glass vial containing a poisonous gas. So what might set the Geiger counter and hammer off? Well, the Geiger counter is set off by a radioactive element. So in here they put a piece of radioactive material that, this guy will set off the Geiger counter on average every 1 hour. Now, sometimes it goes 2 or 3 hours without, setting off the Geiger counter, and sometimes it goes, 2 times in the 1 hour. But over the long-term average, this piece of radioactive material activates the Geiger counter every hour. So what you do is you set all of this up, you put the cat in there, and you put a lid on the box. And then you wait 30 minutes. Okay, so what do you know about the cat? Is the cat dead? Is the cat alive? Well, there's a 50-50 chance that the cat gets it, right? So, because, if you waited an hour, then it'd be approximately 100% chance that the cat died. But after 30 minutes, maybe it went off, maybe it didn't. It's exactly 50-50. So the best way of describing what's happening with the cat is that it's half dead and half alive, right? Now, we can't do any better than that because we can't look in the box. Now, this is similar to what's happening with an atom. An atom is really, 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 really small. And we can only predict, using reasoning similar to what we use for the cat, the probability of where an electron is. Now, with the cat, you could lift the lid off and you would know whether the cat was alive or dead, right? You would be able to answer that. But with the lid on and you can't see into the box, then you don't really know with 100% certainty what's happening with the cat. Now, with something so small as an atom, as soon as we try and look at it, i.e. lift the lid off the box, we actually end up disturbing it and changing it. So it's not possible for us to lift the lid on the box because anything we do to look at a tiny, tiny little atom is going to disturb it. So Schrodinger developed this equation, and one of the things that he found was that his equation will only work if the energy of an electron in an atom is what we call quantized. So when something is quantized, that means that it can only have certain values. So height is quantized when you are climbing stairs. The only time you are stable is when your feet are resting on a step, right? Now, this limits your possible values for height. However, when you're walking up a ramp, you can have a continuum of values for your height. Your height can have any value. There are other examples of this. If you think of somebody playing a piano, then the notes are quantized. You can only play the notes according to the keys of the piano. But if you're playing a trombone, you've got the slide and you can make any pitch of note. So when something is said to be quantized, it can only have certain values. So if the energy of an electron in an atom is found to be quantized, what do we mean by energy of an atom? We mean distance from the nucleus. So we find electrons at some distances, at very specific distances. So no electrons in here, but we find electrons here. No electrons in here, but we find electrons here. No electrons here, but we find electrons here. So in this quantum mechanical model of the atom, the space where the electrons reside is divided into 3 different categories. And these categories are more precise than the next. So it's kind of similar to how a postal addresses work. In the quantum mechanical model, we can describe the shell that an electron is in, the subshell an electron is in, and the orbital that the electron is in. And each is a more precise description than the next. This is similar, like I said, as to how postal addresses work. The broadest category of space would be a state. The next the next smaller unit of space would be the city, and then finally you get down to the street level. So that's what's going on here. Shells are relatively big, subshells are a region within a shell, and then orbitals are a region within a subshell. So we're trying to pin down where the electron is in space about the atom. So electrons in the same shell are approximately at the same distance from the nucleus. So we've got shell 1 here, it's got 2 electrons in it. We've got shell 2, which is further away from the nucleus, and it's got more electrons in it because it's bigger. And then we get out to the third shell, and it has even more electrons in it because it's bigger still. So what we're going to do is we're going to say that the number of the shell beginning at the nucleus and working our way out is going to be indicated with the letter n. So n is just going to be a whole number, 1, 2, 3, and so forth. Really, it just corresponds to the layer of the electrons. And they get bigger as we go out, and so therefore each shell can accommodate more and more electrons as we move away from the nucleus. There's a little formula. The maximum number of electrons in a shell is given by this formula 2n squared. So if I'm in the third shell, if n equals 3, then the maximum number of electrons that I'm going to find in that shell is 2 times 3 squared, 2 times 9. That would be 18 electrons. That's it. That's how this works. Okay. So just illustrating that a little further, we've got, it turns out that there are up to 7 shells in an atom. We number them 1 through 7. They correspond to layers of electrons, and the total number of electrons that it's possible to put into that layer is given by the formula 2n squared, which means you can put 2 electrons in the first layer, 8 electrons in the second, 18 in the third, and so on. Now, it is important to realize that, you know, we haven't witnessed atoms, and we will not be finding atoms where we have completely filled up 5th, 6th, and 7th shells. So the number of electrons that is possible to put into 7 shells would exceed 118. We only need to go up to 118. So within a shell, there are regions of space called a subshell, just like within a state, there are cities, right? So subshells are regions of space within a shell, okay? And electrons within a subshell of a given shell do have the same energy. These subshells are of 4 different types. They're called S, P, D, and F. And these are in increasing size. So S subshells, you can put 2 electrons in those guys. P subshells, you can put 6 electrons into them. D subshells, you can put 10. And F subshells, you can put 14. So they're getting bigger, right, as we go across that sequence. The number of subshells in a shell is just given by the shell number. So shell 1 only has 1 subshell. It's an S subshell. Shell 2 has 2 subshells. It has an S and a P. Shell 3 has 3 subshells, an S, a P, and a D. And then shell 4 has the full set of 4 subshells, S, P, D, and F. Beyond shell 4, we just have a full set of the 4 subshells. So pretty straightforward. Now, what is this little notation that I've got on the side here? We can indicate a subshell using this notation here. This is telling me the shell number. This is telling me the subshell type. So this is saying an S subshell within the first shell. So when I go up here and I write for D, this is telling me the shell. This is telling me the subshell type. So this is saying a D subshell within the 4th shell. So that's kind of cool, right? So it tells you the type of subshell and also where the shell that subshell belongs to. So that's pretty simple. So the shell is the layer of electrons, it's the 4th layer, and then D is telling me the type of subshell within that shell. Okay. Now, within the subshells, we go 1 layer deeper, we're going to find orbitals. So every subshell is comprised of 1 or more orbital. So the orbital describes the region of space within a given subshell, just like a street describes a region of space within a city, right? It's telling you where the electron is most likely to be found within that subshell. The maximum number of electrons that can fit in any orbital is 2 electrons. And S subshells have 1 orbital, so it can hold a total of 2 electrons. P subshells are made up of 3 orbitals and so can hold a total of 6 electrons. D subshells are even bigger. They have a total of 5 orbitals and so they can hold up to 10 electrons. And F subshells are the biggest. They're made of 7 orbitals, 7 times 2. They can hold a maximum of 14 electrons. So it's a pretty simple idea. The number of electrons that a subshell can hold is double the number of orbitals that are in that subshell. So orbitals have characteristic sizes and shapes. The size of the subshell is determined by the n value. As n gets bigger, the subshell gets bigger, okay? The shape, or the orbital gets bigger. The shape of the orbital depends on the type of subshell, whether it's an S, whether it's a P, whether it's a D, or whether it's an F. So S orbitals that make up S subshells have this characteristic spherical shape. So electrons that are in these kinds of orbitals are found somewhere on the surface of a sphere. And the size of that sphere is determined by how big the n value is. Now, electrons that are in p orbitals are kind of weird. They're found within these sort of like teardrop shape, or within these two teardrop shaped lobes. Now, there are three orbitals make up a p subshell. Each of them are at 90 degrees to each other, and each of them have this characteristic shape of being composed of two teardrop-shaped lobes. So there's going to be one orbital along the x-axis, we call that px. There's going to be one of these orbitals along the y-axis, we call that py, and then there's going to be one of these orbitals along the z-axis, we call that pz. So they're at 90 degrees to each other, and you can put 2 electrons in each of these orbitals. So the total number of electrons that can go in your p subshell is going to be 6 electrons. D and F orbitals, they're really complicated as far as their shape's concerned. You don't need to be able to draw these things, but you should be able to recognize a D or an F orbital. D orbitals commonly have 4 lobes, okay? And then F orbitals most commonly have like 8 lobes or more than 4 lobes. So you can kind of recognize them. There is a nice D orbital that looks kind of like that, which is really cool. Whereas the electron is somewhere on the surface of the orbital. That's where it is. Okay, so given diagrams, you should be able to distinguish S, P, D, and F orbitals. Now, an electron has a shell, it has a subshell, and it has an orbital. And these 3 things, they don't tell you anything about what the electron is doing, they tell you about where the electron is. It turned out that Schrodinger had to include a 4th quantity, or a 4th property that described what the electron was doing within the orbital. So what he found was that electrons behave as though they are spinning. And if you remember, electrons are negatively charged, and when charged particles spin, they create a magnetic field. And a magnetic field will have a north pole and a south pole. Now, it turns out that the spin of an electron is quantized, just like its energy, and it only has one of 2 possible values. It spins such that it appears that its magnetic north pole is pointing up, or it spins such that it appears that its magnetic north pole is pointing south. But it's never pointing to the left or the right or somewhere in between. It's just one of these 2 values. Now, how did they figure this out? Well, they took a beam of atoms that have just 1 electron, the hydrogen atom, and then they passed it between the poles of a magnet. And what they found was that half the atoms went up and half the atoms went down to exactly the same extent. Now, if the magnetic poles of the if the electrons were behaving as though they were spinning with randomly, then you'd just get a smear of the electrons upwards and downwards. But no, you only get 2 dots here, which means that they're spinning in one or two of 2 possible orientations. Okay, so now we have a way of telling where an electron is: shell, subshell, orbital. What we would like to do is to write out what's called the electron configuration. which is a description of how many electrons an atom has in each of its subshells. So we're not worrying about the spin and we're not worrying about the orbitals. So we just want to know how many electrons an atom has in each of its subshells. And what we're going to do is we're going to write out all of the subshells from lowest energy, the ones that are closest to the nucleus, to highest energy, the ones that are furthest away from the nucleus, and we're going to indicate how many electrons are in each of those subshells. So we're writing out each of the subshells in order of increasing energy, and then we're going to add a superscript that's going to indicate how many electrons are contained within each subshell. Now, what you want to remember is that an S subshell can have at most 2 electrons, a P can have at most 6 electrons, a D at most 10 electrons, and an F at most 14 electrons. So if we keep that in mind, we'll be on the right track. So S2, P6, D10, F14. So what is this describing here? Well, this is describing an atom that has a total of 2 plus 2 plus 4 electrons. That gives me 8 electrons. It has 2 electrons in a 1s. It has 2 electrons in a 2s subshell, and it has 4 electrons in a 2p subshell. So we could, the 1s is completely filled up with its 2 electrons, the 2s is completely filled up with its 2 electrons, but this 2p subshell has only 4 electrons in it. It could actually have another 2 electrons in there. We can identify what atom this is referring to. Because it has 8 electrons, that tells me that it has 8 protons, because the number of electrons always equals the number of protons. So what is atom number 8? This guy has to be oxygen. This is the electron configuration for an oxygen atom. Okay. So when we build up an electron configuration for an atom that has more than one electron, well, we're going to use what we call the Aufbau principle. And Aufbau is just a German word meaning building up. So what it really is saying is that we're going to organize the electron configuration by putting electrons in the lowest energy subshell first, and then work our way towards higher energy subshells. And remember, what we're really working from is closest to the nucleus to furthest away from the nucleus. So this approach to doing this was devised by a guy called Niels Bohr, who was a Danish physicist. He came up with what's called the Bohr model of the atom. I don't know why he gave this a German name, the Aufbau principle, because he was, like I said, Danish. All right, so this is how the subshells fall with respect to energy. So it starts off quite logical. We got 1s in the n equals 1 shell, and then in the n equals 2 shell we got 2s, 2p. And then in the n equals 3 shell we get 3s, 3p, 3d. In the n equals 4 we've got 4s, 4p, 4d, and 4f. And you can see that the s subshells have 1 orbital, the p subshells have 3 orbitals, the d subshells have 5 orbitals. We get to n equals 4, we get the f subshells for the first time, and they have 7 orbitals. And beyond the n equals 4 level, we don't go higher than the f's. Okay, you can see they haven't written in everything, because in the 6th and 7th subshell we don't completely fill the subshells up. The difficulty is the pattern starts quite obvious, but as we go to higher shells, the layers kind of bunch up, and then when we split these shells out into their subshells, it starts becoming an awful mess, and they start kind of overlapping with one another. And you can see this happening for the first time between the n equals 3 and the n equals 4 subshell. So it would be really hard to memorize the order of energies of the subshells, because it's just so complicated. But fortunately, there's a little trick to get around this. So what we have is what's called the Outbound Diagram, and you should have a picture of this handy, maybe find a picture on the internet and bookmark it on your browser. And it looks like this, the Outbound Diagram. If we weren't doing an online class and you weren't able to have notes for all of your quizzes and tests, you'd have to learn how to draw this. But we write 5s down to 7s, and then next to that we write 2p down to 7p, I'm writing down to 6p in this case, and then next to that we write 3d and down to 7d, and then next to that we write 4f down to 7f, and then the order of filling is we just draw these arrows in diagonally like so, and when we get to the end of the row we just draw another arrow in. And so how we know the order of filling is we just follow along these arrows. When we get to the arrows, to the end of the arrow, we go to the beginning of the next arrow and backwards and forwards and so forth. And that gives the correct energy, the correct sequence of subshells in terms of energy. So that's kind of cool. So find a diagram that illustrates this and make sure you have a bookmark. So now all you have to remember is that in any S subshell, you can put a maximum of 2 electrons. In any P subshell, you can put a maximum of 6 electrons. In any D subshell, you can put a maximum of 10 electrons. And in an F subshell, you can put a maximum of 14 electrons. So makes it kind of simple. All right. So let's have a look at how we can put it to work. So we're going to go across the first 3 rows of the periodic table. So the first row of the periodic table is really easy. It's got 2 elements in it, hydrogen and helium. Now hydrogen has atomic number 1, which tells us that there is 1 electron. So that first electron goes into a 1s subshell. Helium has atomic number 2, so that means it has 2 electrons, and that second electron also goes into the 1s subshell. So now the 1s subshell is filled, and we've got to the end of our arrow, so we have to go back and we have to start on our next arrow. So when we get to period 2, these are the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, up to element number 10. So lithium, atomic number 3, it's got 3 electrons. The first 2 are in the 1s subshell, and then the third one is in the 2s subshell. Beryllium has 4 electrons. The first 2 are in the 1s subshell, and then the second 2 are in the 2s subshell. Now, the 2s subshell is filled now, and we have to go to our next arrow, to the beginning of our next arrow. So what comes next is the 2p subshell. So boron with 5 electrons has 2 in the 1s, 2 in the 2s, and then 1 in the 2p. Now it gets kind of boring now because remember the p can hold up to 6 electrons. So when we come to carbon, well, we have 6 electrons, 2 in the 1s, 2 in the 2s, 2 in the 2p, and then as we work our way across the second row of the periodic table, we're just filling up the 2p until it has 6 electrons. Now once that's filled, we're going to move on to the 3s. So period 3 is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So sodium with 11 electrons, it has everything that neon has, which is 10 electrons, plus 1 more, and that extra electron is going to go into the 3s. Then magnesium has 12 electrons, so it has the 10 that neon have, and then it has another 2 electrons in the 3s. But now the 3s is filled because S subshells can hold 2 electrons, so we have to go over to the 3p. So aluminum has the 10 electrons that we found in neon, 2 that are in the 3s, and then it's got 1 in the 3p because the 3p is what comes next. So silicon has 1 more electron than aluminum, so that goes into the 3p. Sulfur has 2 more electrons than aluminum, so they go into the 2p, and we keep going until we fill the 3p up. The 3p is full when it has 6 electrons, and that's when we have argon with a total of 18 electrons. 10 are in the same configuration as found in neon, and then we've got 2 in the 3s subshell and another 6 in the 3p subshell. So now we move on to the 4s. So we'd go 4s, fill that guy up with 2 electrons, and then we'd start on the 3d, and the d, if you remember, has 10 electrons. So that would go 3d1 all the way up to 3d10. Okay, so hopefully you'll get a little bit of practice using the Outbound diagram, and you'll be able to write out the electron configuration for any atom. The important thing to remember is that an S subshell can have a maximum of 2 electrons, a P subshell can have a maximum of 6 electrons, a D subshell can have a maximum of 10 electrons, and an F subshell can have a maximum of 14 electrons.